Concept 9. Stress visualization in thin pressure vessels. The three types of stresses in the case of a close pressure vessel are longitudinal or axial stress, hoop or tangential or circumferential stress, and radial stress. Out of these three stresses, for a pressure vessel, radial stress is considered negligible as it is a plane stress condition. Making a general comparison for thin pressure vessels between loads in hoop and longitudinal directions, hoop load is greater than the longitudinal load. Let us now derive an expression for longitudinal stress. We know that stress equals force by area and force equals pressure into area. The force that causes longitudinal stress is the force that acts on the end lids or plates of a cylinder. Hence, force equals lid area into pressure on the lid, which is pi d square by 4 into P. The figure shows internal pressure in the longitudinal direction. The material cross-section of the pressure vessel that withstands longitudinal stress is given by pi dt. Longitudinal stress equals force by area, which equals pi d square by 4 into P by pi dt. This equals Pd by 4t, which is Pr by 2t. Let's now explain hoop stress in detail. The internal pressure is acting on the area across the length of the vessel, pi RL, which is the inner curved area of the cylinder. The hoop force is computed by computing the projected area for half the cylinder. The vertical parting plane is perpendicular to the parting hoop forces, and the plane can exist along any diameter as the hoop stress is uniform throughout the material cross-section. In order to calculate the horizontal hoop load, we need the horizontal component of pressure multiplied with the area on which it is acting. Two symmetric arbitrary points A and B are chosen as shown in the figure. The pressure force F at each point equals P into delta A. The pressure force is resolved into vertical and horizontal components. By symmetry, the vertical components cancel each other, whereas the horizontal components add up. If you add all the horizontal components across the curved area of the cylinder, we get horizontal hoop force that is trying to part the cylinder along the vertical plane. Mathematically, the addition of horizontal components is found by doubling the following integral. Hoop force equals 2 into F cos theta. This is integrated between the limits 0 and 90. Substituting P delta A for F, we get the expression as shown, where delta A equals R d theta into L. Replacing this in the expression, we get hoop force as shown. Simplifying, we get the following, which equals 2 PRL sin theta between the limits 0 and 90. Substituting the limits and simplifying, we get hoop force to be 2 PRL. Let's number this equation as 1. The hoop force in equation 1 is resisted by the hoop stress acting normal to the areas as shown in the figure. The hoop stress is therefore given by hoop force by areas, which equals 2PRL by 2TL, which equals PR by T. It can be observed that hoop stress is twice that of longitudinal stress. Note that hoop strain is not twice that of the longitudinal strain, and hence it cannot be interpreted as we do for stresses. This is a biaxial stress state, and hence the Poisson's effect needs to be considered to compute strains. The actual ratio of strains is as follows. Hoop strain is as follows, and longitudinal strain is as follows. Grouping and dividing hoop strain by longitudinal strain, we get the following equation. Taking ratio of hoop and longitudinal strains, we get the following. Substituting the fact that longitudinal stress is half of hoop stress and hoop stress is twice that of longitudinal stress, we get the following. Simplifying, we get 2 minus nu by 1 minus 2 nu. If the Poisson's effect does not exist, then the ratio is 2:1, which turns out to be the same as that of the stress.